Hello, my name is Wendell Boucher. Hopefully this is the first of a series of tutorials addressing switch mode power supply design. This particular topic was chosen because it's rather badly misunderstood in the industry, because very few switch mode power supply designers actually design their own transformers. The title of this one is Reducing Transformer Copper Losses Due to Skin and Proximity Effects. What we are showing you here are two winding configurations with exactly the same winding build, which means the dimensions of the transformers are identical. If you look on the left, you'll see that the wire loss, copper loss, is 8.4 watts at 100 kilohertz at that single frequency. And on the right, you see the same build, but a different winding configuration. And you can see that the wire loss here is 1.08 watts at 100 kilohertz. That's a reduction to 12.9% of the copper loss of this configuration, which is significant. And all we've really done is construct the transformer, but connect the windings together in a different way. Now we're going to show you how this is actually done and why. But first we have to come up with a few definitions for you. We're going to be using a system of equations to calculate the copper loss for a practical problem using the so-called GE calculations, and they agree within 10% of FEMM calculations if the following conditions are true. The field between the layers of copper has to be as linear as possible and practical. This means that the ratio of winding length to insulation thickness is 100:1 or higher. And second condition is that all winding layers are the same winding length, called traverse, and centered on one another. And here you see an example. Here's a layer of copper wire, another layer of copper wire with insulation between the two layers, called insulation thickness here. And if we divide this winding length in inches by insulation thickness in inches, we'll find, usually in practice, that we're meeting this condition. It's not a magic number. It doesn't mean it won't work if it's 50:1, though the error might be a little bit greater. It might be 12% up here if you do that. We prefer to see a figure of 100:1 or higher, as I said. Now, what's very important is a parameter called the M factor and the KP factor. For this discussion, the major goal is to reduce the H field, which we define for you, the H field magnitude, by making the M factor equal to 1 for all layers. Now here's the significance of the M factor before we actually start with the examples. The M factor controls the KP factor, or you can say it another way: the KP factor is a function of the M factor. This is what we're going to actually control. The KP factor comes from the equation when we execute it. And if we were to take, for example, AWG, number 24 wire, means American wire gauge. Here's the meaning of the KP factor. We multiply RDC by the KP factor to produce a number called RAC. Then the copper loss is IAC squared times RAC. And if we have a DC component, we would square that and multiply it times RDC and add the two together. Here's the real significance of the M factor. For example, at 100 kilohertz, we plot or show M and Kp. If M is 1, Kp is 1.58. If it's 2, it's 5.84. If it's 5, it's 44.21. Look at the difference between these two numbers. This is the reason we strive to make M equal to 1 in any transformer design using copper wire. And if you see at these different frequencies, for example, look at 500 kilohertz, M a value of 1 gives us 3.83 for Kp, but a value of 5 is 166.59. That's a huge number. Therefore, I'll say it again. We're going to control the H field magnitude by making the M factor equal to 1. Now, we'll give you an example. Take a quick look at this build diagram, perhaps the one on the left. I'm going to slide this down, and you can see that we simply copied it on the left, winding build diagram. So the first step is to take that build diagram and rotate it 90 degrees clockwise. Reason for that is because we want to fetch these winding layers, because we're going to use those for the calculations. I've taken the liberty of doing that already. And by the way, the layers that are associated with the primary are called the primary winding layers, or the primary winding for short. The same for the secondary layers. I've repeated this again because it's so important. The major goal is to reduce the H field magnitude by making the M factor equal to 1. Now, here's the worst case condition for that transformer, which of course is this one on the left at 8.4 watts. And this is the best case when we reconfigured the transformer to reduce that copper loss. I've taken the liberty too of using different colors. This is the primary winding, the secondary winding in red, primary winding in yellow, secondary layers or winding in red again. And now I'm going to show you exactly how to calculate these losses. Looking at the winding configuration on the left, what we do is to assign relative power levels to each layer. These are all layers. So let's start with this pen color. We'll call this 1 power level, 1 unit for each of these. And for the secondary, we'll call it -1 unit. -1 unit, -1 unit, and -1 unit. Now here's a rule you have to follow. This, you can consider this as a wattage, so we'll call it watts. I want to explain to you right now how we do that. Normally when you look at the H field, you use ampere turns per meter or ampere turns. We've converted that to watts. It's much more convenient to use. This is the wattage level. When we take power from the transformer, that's a secondary, and we use a negative value for that number. Another rule is that always has to equal 0. For this one, we have 1, 1, 1. Fix that a little bit. And 1, that's the power going in, -1, leaving the transformer. And again, this has to equal 0. Reason for that is because the H field at this point in the winding and at this point in the winding, for both cases, is 0. I'll show you up above again. The H field here is 0. The H field here is 0. H field here is 0. and the H field here is 0. That's the nature of closely coupled windings. Now, how do we draw the H field? It's relatively simple once we have these numbers. I will be going over this a little more in the future in this tutorial, explaining how we develop this, of course. For now, I'm just going to do the work. I'll draw the H field by hand, I think, using this pen. What we do is draw a straight horizontal line, as straight as we can, and we see a unit which is not negative but positive, which that is. When we come to the wire, we move up 1 unit. Then we move over in the space between the wires. We move up, I should say, 1 more unit. Space between the wires. Move up 1 unit. Finally, move up 1 more unit. When we come to the secondary, however, or when we see any negative number, we go down 1 unit. We go down 1 unit, over, down, over, down, over, down, and finally a horizontal line again. Now, before we do anything else with this, let's do it again over here. Horizontal line. We go up 1 unit. Space. We go down 1 unit. Over. Down 1 unit again. Over. Up 1 unit. Over. Up 1 unit. Over. Down 1 unit. Over. Down 1 unit. Over. Up 1 unit. And finally that horizontal line. Now let's put some numbers down here. We know the H field is 0 here. And H equals 0 here. And H equals 0 here. So we put a 0 here. Look for any other zeros we can find. We can find no other zeros except this one for this plot. And for this one, we have a 0 here. We have another 0 here. Another one here. Another here. And another here. A lot of zeros. Well, we already showed that one. Now, what do we do next? We start at a point of 0. And we move up as far as we can move upward. You see a staircase in some cases. Here you don't see one, but yes, we do. It's just 1 step, though. So we start at 0 and move in any direction we can move to increase that value. And as we do that, we show an integer of 1. Next time it's 2. Next time it's 3. Next time it's 4. If we had more of these, it'd be 5, 6, and 7. So we're finished with that. Let's look at this one. We start at 0 again, go upward 1. Next time we go up, it's 2, and next time it's 3. Next time it's 4. Now let's look at this one. We go 0, but we can increase that number only to 1. 0, only to 1. 0, you'd normally think this is -1, but we're going to use magnitude. Just keep that in mind. So it's 1, 0 to 1, 0 to 1, 0 to 1, 0 to 1 again, and finally 0 to 1. Now, here's the definition of M. All of these numbers are the M factor. This is what we're trying to do. Make the M factors always 1. Here the M factor goes as high as 4. So let's move up just for a moment, see what that means. Look what happens when the M factor is 4. The multiplier for the DC resistance is 27.16. If it's 1, it's only 1.58. That's a big difference. So what have we really shown here? We've shown that this is the H field. Plot. This too is an H field plot. And you saw how we did that. Now what's the meaning of this when we do it this way? I'll show you. If we show the build diagram now as vertical, and we show the secondaries in red, here and here, of course, that line for you. And if we calculate the watts of copper using the M factor, you'd see that these are the wattages. Now I'm going to show you the program that does that. This is a program written in a language called JustBasic. It's up here. This is a free program you can download. I've written this program in JustBasic, and it's available to you just for the asking. You can see we input the data right here. I'll move this around, try to get your attention up at the top. American wire gauge, you simply input a number. And if this is a real design, you would know the mean length of turn. You would know the number of turns, you know the temperature, or you can estimate it. And you know the RMS current. You also know the frequency. And you know the value of M simply from this diagram we showed here. That's where we get the M from. So if we actually plotted this, let's run this program. Let's say we want to know where M is 1, what is the dissipation for that layer. We run the program, M is 1, click right here, and here's the solution, 0.135 watts. Remember that number? 0.135 watts. Now since M is always 1 here, that means the dissipation is always 0.135 watts. So the total dissipation for this best winding configuration is 8 times that. There's 8 layers. 8 times 0.135 is 1.08 watts, which is the number we gave you before. Now let's look at this one. Let's say M is 2. Simply change M to 2. Run it again. See, we have 0.499 watts. Remember that? 0.499 watts. 0.499 watts. This one's also 0.499 watts. And as we go up, it goes 0.499, 1.227. Finally, but an M factor of 4 is 2.32 watts for that winding. Let's do that one. To make it 4. $2.32 watts. 2.32 watts. You add all of this up and you get 8.362 watts, which is close enough to 8.4 watts, which I think is the number I gave you in the very beginning. There it is, 8.4 watts. Now, I think you've learned something at this point, that that if we're not careful how we wind copper layers and connect them together, we can be in big trouble. For example, this is the way someone would probably normally wind this transformer without thinking about the M factor and the H field. You'd wind a primary, put some insulation in there, then you wind a secondary. And you can see how much trouble you would be in. Now I'm going to erase this and give you some other winding examples because it's important to know what to do. So let's erase this. And start here again. Now here's another winding configuration. Just ignore that. You shall see fairly often. Well, I'll show you the reason for it now. We'll use the same color for the time being. Let's say we have, for relative wattage, unit of 1, unit of 1, unit of -2. Remember, it has to equal 0. What's the H field look like? Move over, move up 1 unit, over, up another unit, and over here, we go down 2 units. This is 0, this is 0, the only 2 zeros we can find. We move upward, put a number 1 there. Move upward, put a number 1, next one, number 2. Because we have a 2 and we don't have a 1, we'd like to get rid of that 2. That's not a good idea. So briefly I'll show it again over here. There's a way to do it. -1, 2, -1. The H field flood goes down 1 unit, comes over here, goes up 2 units, comes over here, goes down 1 unit, back to our zeros again, which is absolutely necessary. But what do we have here? We have a 0 here. We go down 1, go from 0 to down 1, 0, up 1, 0, up 1. And this looks just great. That's what we wanted to do. But we have a problem. If you look at this wire, and you look at this wire, we have the one on the left, the one in the center, the one on the right. If you're looking at the edge of the wires, you'd find that the H field was actually penetrating the wire like this. Same for this wire. But for this one, it's only penetrating here and only penetrating in here. In that area, H equals 0, as you can clearly see from this. This is one wire. This is one edge of the wire here. This is the left edge of the wire. So in the center, it's 0. So we have to have some way to deal with that, especially if we're going to run this program. Okay? So here's how we do it. I'm going to erase this and give you a procedure which is very simple. What we do is draw the 3 windings we had. -1, 2, -1, like we did. And then we redraw it down here. And we replace this one with 2 layers, 2 windings, if you will. So this is now -1. This is 1, this is 1, and -1. Now we have an H field here, that looks like this. Down 1. We go up 1. We go up 1 again. And we go down 1. Actually, you could build a transformer this way, but it's a little more complicated. H field is 0 here. We have 1 here. 1. All 1s, which is good. Now, the next step, and I want to explain this rather carefully to you, is that this is the actual design. This is the actual design. And this is the calculated design. We're going to use this one to calculate the losses. But we're going to build this one. Because that's an easier one to build. Now, how do we, one more step we have to give you. We'll give it to you right here. Let's say this is the original design again. 3 windings. And then we're going to have this one. All we're going to do is change what we do right here. We're going to replace it with this. This stays exactly the same, but what we do is note that the AWG equals X. In this case, it equals number 24. That's what we have in the program. Number 24 wire. See it right here? Now what do we do here? Each of these is now X is AWG is a value of X plus 3. So the wire size we would use here would be AWG number 27. AWG number 27. When we make those calculations using a finite elements analysis program, namely FEMM in this case, we get, when we do it this way and compare it, the comparison is within 4%. So it's a pretty good solution process. I feel it important to mention this too, that in the real world with switch mode power supply design, we're working with quasi-square waves and almost square waves. In hard switching, this is a hard switched 500 watt 2-switch forward converter, just to give you an example, with a peak current of roughly 1 ampere. This is a spectra produced by that power supply. This is the current passing through the primary of the power transformer. That means that if we want to really calculate the losses accurately for a transformer with copper wire, or in fact any other conductor material, for example copper tape or Litz wire, we would calculate over this range of frequencies down to about 5% of IP. In this case, we'd have to calculate for about 12 to 15 frequencies. If you're doing it with this program, that means you'd have to run it 12 or 15 times for each layer, which is a lot of work, of course. So you can see that I'm just demonstrating to you how we do the work. In the real world, I do this with a program that reads all of this data and executes it in one single program. One to a copper wire, one for Litz wire, another one for tape. Now here's a 2 kilowatt LCC resonant converter. You can see the peak current's about 14 amperes. Can't see it very clearly, but that's what it is. Here we only need to calculate at the fundamental frequency and for all practical purposes the third harmonic. We have to make 2 calculations. What are the benefits of using resonant topologies? We're almost finished. I want to show you some very important observations. I've seen this done a number of times and it's totally incorrect. If we were to consider just the skin depth at 100 kilohertz, we would find that the RAC of another 24 wire is only 3.4% times the RDC, fairly low number. If we then use that figure to calculate the copper loss for each of the 4 layers, for the primary and for the secondary, the total copper loss would be 0.703 watts, which is a very low figure. And the reason I bring this up is because I've seen designed based on this theory, which is totally incorrect, as I said. And when they talk about it, they say you can use any number of layers, doesn't matter. That's also very incorrect, you just saw. So we'll compare this 0.703 with 1.08 watts, which is the best we can possibly do for this particular example. But if we were to wind the transformer the worst way, which would probably be the way you would do it if you didn't know enough to calculate the H field, look at the M factors, you'd have a loss of 7.84 watts. Is way away from 0.703. I don't think I said this before, but the G equations were last published in 1964 and earlier in 1952, and the reference is a document entitled High Power, High Voltage Audio Frequency Design Manual. The earlier publication focused on pulse transformers. And the GE equations were actually derived from work done in 1903 by a man by the name of A.B. Field. That's the source for all of this information. And Dartmouth University is doing work right now, as I speak, to improve the GE equation with fudge factors, if you will, that allow for different separation between turns and different separation between wires. Unfortunately, I don't have that data. I should have their conclusions. One feature of this free program I'll give you if you ask for it is a wire table is generated by using this simple set of equations. And this is the GE equation right here, at least down to this point. This is the KP factor. It's a function of all these other parameters. And finally, or almost finally, I sincerely hope that this presentation was helpful and interesting. My current goals are threefold, and they're quite different. The first one is to help younger folks as young as 14 years of age. I started when I was 13. I was a ham radio operator, got my license, doing how to design circuits and transmitters at that age. So you can start pretty early in this field if you're interested. Anything I do for you fun folks will be free, of course. And to present more technical videos to engineers and technicians practicing in the field who have concerns and questions in my field, namely power electronics design. I've been in other fields, but that's my latest field for the last 30 years or so. And you can get topics to consider looking at my resume and looking for suitable topics as you wish. I'll show you that resume in just a moment. Also, I am semi-retired and am doing consulting in these fields, and I'm looking for work there, of course. If you want to see more videos such as this one, then please contact me with the following information: the subject you're interested in and why, so I can better tailor the video for you. I'll also send you at no cost, anytime, all applicable source computer programs that are created to save you time. Your feedback is much appreciated. My home is in Bristol, Virginia, in the United States, and I can be reached via YouTube, my email, or my home phone. I'll bring this back for you in just a minute to view, but you can take a look at my excerpts from my resume. The only reason I'm showing these to you is to give you some ideas for topics. Modeling and simulation, very strong field. Closing feedback loops is another, and designing magnetic devices is another. Some of my accomplishments include these patents in the communications field as well as the power field. Books I've written, a couple on mathematics, and of course resonant power supplies and magnetics again. And before I was in this business, I spent some time designing filters, and I started when I was a very young man at radar, when radar was a very popular subject. I'll bring up to this last one, leave it there for a couple of seconds, and then shut down. I hope you enjoyed this video. My purpose in presenting it was to help you reduce power losses in transformers. Talk to you later. Bye-bye for now.